Hello and welcome to your lesson today on mutually exclusive and non-mutually exclusive events. These are questions that are going to focus on the word or, and hopefully remember or means add. Add. And there will be some questions that combine or and. So there will be some questions where there's multiplying and adding. So the symbol for or is this symbol right here, and it stands for union. So it's the union of set A and B. And one thing you have to be careful of, it's the probability that the outcome is in either event A or event B or both. So it counts A only, it counts B only, and it counts both. So the entire thing is A or B. Please keep that in mind. Some people think it's only A and only B, but it also includes the overlap. So to find the probability, what we're looking for are the number of outcomes that are in A or B. So all of the circle parts divided by the total number of outcomes in the sample space. Now, there's a difference between mutually exclusive and non-mutually exclusive. So with mutually exclusive, that means there is no overlap between the two sets. So they have no outcomes in common. So for example, if you draw a card from a standard deck, what is the probability that it is an ace or a king? Well, there are no cards that are aces and kings, both of them. So these are mutually exclusive events. So if we're going to let A be drawing an ace, and K be drawing a king, then the probability of drawing an ace or a king is the number of aces or kings divided by the total number of cards in the sample space. So the number of cards that are aces or kings, well, or is add. So there are 4 aces, there are 4 kings out of a total of 52 cards. That works out to 8 out of 52. And that works out to 2 over 13 in lowest terms. Now another way you can do this is rather than just counting the outcomes, because we're looking at the probability of A or B, what we could do is just add the probability of A and the probability of K. So the probability of an ace is 4 out of 52, and the probability of a king is 4 out of 52. And when you add fractions, you keep the denominators the same, you just add numerators. So that's still going to give you 8 out of 52, which is 2 over 13. So just pretty much the same math, just 2 different ways of looking at how to approach the question. Alright, so if the events are mutually exclusive, then all you have to do is add their probabilities. It's when the questions are not mutually exclusive that we have a bit of a problem. So let's take a look at this example. Non-mutually exclusive are events that have things in common. So for example, if we were going to draw from a standard deck, what's the probability that it's a heart or a king? Well, these are all the hearts, and these are all the kings, and there are cards that are hearts and kings. So we do have some overlap here. So what we have to do here, start with our let statement. So H is drawing a heart. And K is drawing a king. So the probability of drawing a heart or a king. Now we talked about this a little bit in Unit 1. In Unit 1, we learned how to figure out the number of hearts or kings. When there's overlap, if you remember, you have to take the number of hearts and you have to add the number of kings. And hopefully from Unit 1, you have to remember that this king of hearts got counted as a heart, and this king of hearts also got counted as a king. So you have to subtract the number that is a heart and a king. And that's all over the number in the sample space. So there are 13 hearts, there are 4 kings, there is 1 card that is overlapped, and that is out of 52, and that works out to 16 over 52, or 4 out of 13. Again, same math, just a little bit of a different approach. You could look at this as being, so the probability of H or K is the probability of a heart plus the probability of a king minus the probability of a heart and a king. So the probability of a heart is 13 out of 52. The probability of a king is 4 out of 52. And the probability of a heart and a king is 1 out of 52. And that's still going to give you the same answer. So the math is the same, it's just which way you want to write it. Now, the issue here is this is what a lot of people will forget to do. They will add the hearts and they will add the kings because the question says or, but they will forget to do the overlap. So please, you got to think about whether this is mutually exclusive or non-mutually exclusive, and if it's not mutually exclusive, you've got to subtract that overlap. So that's the formula for non-mutually exclusive. It's probability of A plus the probability of B, but you've got to subtract that overlap. Now, to calculate that overlap, sometimes you can just count how many outcomes there are like we did here. Sometimes, because this is A and B, if the events are independent, you can calculate it just by PA times PB if they're independent. And if the events are dependent, then that would be the probability of A, and from last video, it's the probability of B given that A occurred. So that's if dependent. So sometimes to get the overlap, you can just count how many there are. Like in this question, we can just count that there's one that's overlapped, but sometimes you have to actually do one of these calculations. So let's look at the next example. 2 dice are rolled. What is the probability of rolling a sum of 7 or a sum of 10? So S is rolling a sum of 7 and T is rolling a sum of 10. So if you take a look at the sums of 7, there are 6 of them. And if you look at the sums of 10, there are 3 of them. And there is no overlapping here, so these are mutually exclusive events. So to find the probability of a sum of 7 or a sum of 10, you just need to add them. So the probability of a sum of 7 is there's 6 out of 36. And the probability of a sum of 10, there are 3 out of 36. So that makes 9 out of 36, which is 1/4 in lowest terms. So there's a mutually exclusive example. We'll take a look at a non-mutually exclusive example. 2 dice are rolled. What's the probability of rolling a sum of 10 or doubles? So we'll let S be rolling a sum of 10, and we'll let D be rolling doubles. Now doubles means that both dice are the same. So right here are the outcomes of rolling a 10, and along this diagonal are the outcomes for the doubles. So 2 1s, 2 2s, 2 3s, 2 4s, 2 5s, or 2 6s. And you can see right here we've got some overlap. So that means these are non-mutually exclusive events because you have overlap. So the probability of a sum of 10 or doubles is the probability of a sum of 10 plus the probability of doubles minus the probability of the overlap, sum of 10 and doubles. Please don't forget that overlap part. So the probability of a sum of 10 is 3 over 36, and the probability of doubles, there are 6 of them, and the overlap, there's 1 that's overlapped, so that is 8 over 36, and in lowest terms 2 over 9. So there's some knowledge questions that involve or either mutually exclusive or non-mutually exclusive. And now what we'll do is we'll take a look at some examples that are more application based. So the probability of Billy Bob getting a good mark in advanced functions is 85%, and the probability he gets a good mark in data management is 90%. The events are independent. That's important to know. To get into university, he only needs one grade 12 U course. What's the probability that he will get a good mark in either course? We're going to illustrate with a Venn diagram. So let's start with this. Here's your Venn diagram. We're going to let A be a good mark advanced functions, and D is a good mark in data management. So this is A and this is D. Now, the reason we know that they overlap and that they're not mutually exclusive, so these are non-mutually exclusive. Sometimes you have to think a little bit. If there's overlap, that means it is possible to get a good mark in advanced functions and get a good mark in data management. So you have to think logically, is it possible to get a good mark in both of them? Of course it's possible. So that's why there is overlap here. So because these are non-mutually exclusive, the formula for getting a good mark in advanced functions or data management is the probability of getting a good mark in advanced functions plus the probability of getting a good mark in data management minus the overlap. Now the probability of getting a good mark in advanced functions is 0.85, and the probability of getting a good mark in data management is 0.9. Now, this is where you have to use a little bit of math because we don't know what the probability of the overlap is. But because we know that the events are independent, the probability of it getting a good mark in advanced functions and data management can be found by multiplying them because they're independent. So that would be 0.85 times 0.9, and that equals 0.765. So you would have to subtract 0.765 from that. So when you do this math, you get 0.985. If we were to label this Venn diagram, we just found out that the middle part was 0.765. And since we know that the probability of getting a good mark in advanced functions, the entire circle is 0.85. If you subtract 0.765, then that means just this section, which is A only, would be equal to 0.085. And the same with data management. Getting a good mark in data management is 0.9, but that's the entire circle. So to just get data management only, you would have to subtract 0.765, and that would give you 0.135. So getting a good mark in advanced functions only is 0.8085. Getting a good mark in data management only is 0.135, and getting a good mark in both is 0.765. So another way you could have answered this question rather than using the formula is fill out the Venn diagram, and then the probability of getting a good mark in one or the other is 0.085 is getting a good mark in advanced functions only, plus 0.135, which is the probability of getting a good mark in data management only, plus, remember, or considers both as well, getting a good mark in both. And that also works out to 0.985. So that's just an alternate way you could have answered that question. So for labeling this part here we said was the probability of A and D. This part here, which is just A, there's a couple of different ways that you can label this. The first way you can write this as this is the probability of A but not D. So that's different than the given line. That's a diagonal line and it slants downwards. So that's the probability of A but not D. Or you can write it as the probability of A and not D. Oops. A and not D. And both of those just means basically A only. Similarly, this label here, you could write this, that 0.135 is the probability of D but not A. Or you can write it as the probability of D and not A, and that means D only. So just a little bit of labeling for you. So this here is the probability of A but not D. This is the probability of D but not A. And this is the probability of both. So, different ways to label this. Next question. This question I want you to put a star on because you will see it in some of your homework. You will see it in some of the practice sheets, and I can guarantee you will probably see this on the test. So, this combines ands and ors and conditional probability. So we have all three things. What you want to remember is the formula for conditional probability. So the probability of A given B is equal to the probability of A and B divided by the probability of B. Right, so please make sure you know how to do this question. So, it turns out that 10% of the population is Martian. Most of these Martians are unaware that they are not human. For this reason, a test was devised to detect Martianality. When a Martian is tested, the result will be positive 85% of the time. When a human is tested, the result will be positive 5% of the time. And when it says positive, that means positive for being a Martian. So that doesn't mean they're testing positive, a human being tested positive for a human. A positive test means that you're testing for, the test shows that you're a Martian. So an individual is selected at random and tested. What is the probability that the individual chosen will test positive? So what we're going to do is start with a tree diagram. So in the beginning, you're either a Martian or you're not a Martian. So let's let M represent being a Martian. And it says that 10% of the population is a Martian, which means 90% of the population is not a Martian. Now, Martians and non-Martians, which are humans, are given a test. A p means that you test positive for being a Martian. So this is not testing positive. This is testing positive. This is not testing positive. So it says, when a Martian is tested, the result will be positive 85% of the time. So this is 0.85. So a Martian will test positive for being a Martian 85% of the time, which means 15% of the time the test is wrong. When a human is tested, the result is positive 5% of the time. So if the person is human, 5% of the time, the test will still say that they're a Martian, which means 95% of the time, the test will say they're not a Martian. Now, the probability of P here is 0.85, so the probability of testing positive is 0.85. This probability of testing positive is 0.05, so those are not equal. So this is where we have conditional probability, because these are dependent events. So this is testing positive given that they're a Martian. This is testing negative given that they're a Martian. This is testing positive given that they're not a Martian, so that's given that they're human. This is not testing positive given that they're not a Martian. So this is testing positive and being a Martian, testing negative but they're a Martian. This is testing positive for a Martian but they're human. This is testing negative for a Martian and they're human. So that's what that all means. So the question says, what is the probability that the individual chosen will test positive? So we are looking for the probability that they are going to test positive. So there are two branches in which the person will test positive. They can be a Martian and test positive, or they could be a human and test positive. So that's why this is an or question, because we have two cases. You can be a Martian and test positive, or you can be a human and test positive. So our two cases would be being a Martian and testing positive given that you're a Martian, or you could not be a Martian, which means you're human, and you test positive for being a Martian even though you're human. So, probability of a Martian is 0.1. Probability of testing positive is 0.85. Or, probability of not being a Martian is 0.9. And the probability of testing positive even though you're not a Martian is 0.05. And that works out to 0.13. Alright, so that's question 8. That's just what's the probability they tested positive. Now, in this case, this is a conditional question. What is the probability that the individual chosen is a Martian given that they tested positive? So this means if the test showed that they were positive for being a Martian, what's the probability that they actually are a Martian? So if you take a look at your tree diagram, remember the formula for conditional probability. So the probability of being a Martian given that you tested positive is the probability of being a Martian and testing positive divided by the probability of testing positive. So the probability of being a Martian and testing positive is this branch right here. So it's being a Martian and testing positive. So that's what goes on the numerator. In the denominator, it's the probability that they test positive, which is what we actually just calculated up here. So there are two branches where they test positive. This branch and this branch. So the probability of testing positive could be being a Martian and testing positive, or being a human and testing positive. We could have just written 0.13, but just thought I'd write it out again. So this works out to 0.085 over 0.13, and that is approximately equal to, when rounded, 0.654, which is basically about 65.4%. So that kind of gauges how good a test it is. So if they tested positive for being a Martian, there's only a 65% chance that they actually are a Martian. And because we rounded, don't forget to write the word approximately, 0.654. Don't forget your approximately equal to signs. And just so that you don't make mistakes, these aren't just squiggles that you can design any way you want. They are called tildes, Tilde, and it goes up, down, up, up, down, up. So you can't just make squiggles any way you want. You got to make sure that your squiggles are going the right way. So it's a double tilde, and that's that squiggle that is on your keyboard. So there is a question. You're most definitely going to see it, so make sure you know how to do it. It combines and, it combines or, and it combines conditional probability. So what you're going to do now is what you normally do. Pause the video, and you're going to try these questions, and you're going to come back and check your answers. So press pause and come back and check later. Okay, welcome back. Let's just check your answers. In question 1, it was just a straightforward probability of a spade or a face. So it's the probability of a spade plus the probability of a face minus the probability of both. Works out to 11 over 26. Now, for question 2, the probability of Billy Bob getting accepted to U of T is 0.75, and the probability of him getting accepted to Queen's is 0.8, and the probability of him being accepted to both is 0.65. So we're letting U be getting accepted to U of T, Q is getting accepted to Queen's, and the question is, are these events independent? So to know if they were independent, knowing the independent formula is that if you multiplied the probability of U and the probability of Q, you should get the probability of both, which is 0.65. But when you multiply the two of them together, you get 0.6. So because when you multiply U and the probability of U and the probability of Q, you do not get what the overlap gives you, that means they are not independent. In B, it says, are these mutually exclusive? Well, first thing is you can think about it is that it's possible for them to get accepted to both. But numerically, and this is something I want you to think about because a lot of people will do this, when you add the probability of getting into U of T and the probability of getting into Queen's, you get 1.55. Probabilities cannot be higher than 1. So if you're getting a number that is higher than 1, then that's wrong. So obviously you have to have some sort of overlap that you would subtract to bring this number to be less than 1 because probabilities cannot be over 1. For question C, two ways of doing this because it's probability of U of T getting into U of T or Queens, so it's the probability of U of T plus the probability of Queens minus the probability of both, and it says what each of these numbers are in the question, so that's 0.9. If you were to do it the second way that I showed you using the Venn diagram, both is 0.65, so U only would be 0.1 and Q only would be 0.15. So if you added U but not Q, so that's U only, which is 0.1, plus Q only, which is Q but not U, which is 0.15, and added them both because OR includes both, you also get 0.9. Now a little bit of a twist to this question. Rather than saying just OR, this is saying he will only be accepted to 1, which means not both. So that means you're only looking for the U only and the Q only. So it's the probability of getting into U of T but not Queens, which is 0.1, plus the probability of getting into Queens but not U of T, which is 0.15. So that works out to 0.25. So do make sure you know the difference between these two questions. Question 3 is similar to question 2. So B is the probability of B is making the basketball team, Q is passing the math quiz. So the probability of making the basketball team and passing the quiz, because they're independent, and means you're allowed to multiply the probabilities, so that gives you 0.6. Remember that you cannot multiply the probabilities if they are not independent. If they are dependent, this would have to be a conditional probability. So B is similar to what B was in the previous question. To make the basketball team or pass the quiz, you can use the OR formula. So it's the basketball team plus the quiz minus both. But in this case, both, because they're independent, is 0.75 times 0.8, which is actually what you calculated up here. Or you could do it the other way I said. If both is 0.6, baseball team only is 0.15, quiz only is 0.2. So you could look at the basketball team but not the quiz is 0.15. Probability of there being a quiz but not making the basketball team is 0.2, plus the probability of both, because OR includes both, 0.6. They both give you 0.95. For question C, now in this case there are two ways to answer question C because they are independent events. So you can answer question C the same way we answered 2C, where it's B only plus Q only. So it's the baseball, probability of the baseball but not quiz, plus the probability of quiz but not baseball, but not both. So you do not want to include that 0.6. But because these events are independent, you can use multiplication. So you could take this 0.15 could be found by making the basketball team and not passing the quiz. So this 0.75 times 0.2, that is actually, let me just move this down, that is actually 0.15, which is where this number comes from. And I should say, or having a quiz and not making the baseball team, 0.8 times 0.25 would give you 0.2. That's where that comes from. So you're still getting the same answer. It's just a different way of answering the question. But this method can only be done if the events are independent. If they are not independent, you have to use the first method. Question 4 was just like the Martian question. So the probability that the bus being on time is 0.9, so not on time is 0.1. If the bus is on time, the probability that Jim will be on time is 0.95, so the probability that he'll be late is 0.5. If the bus is late, the probability that Jim will be on time is 0.45, so the probability he'll be late is 0.55. So this is conditional. So what is the probability that bus is on time given that Jim was on school? So this is conditional. So the probability that the bus is on time given that Jim was on time is the probability that the bus is on time and Jim is on time, which is this branch here, 0.9 times 0.95, divided by the probability that Jim was on time. So there's two branches where Jim is on time. So it could be bus on time and Jim on time, or bus late and Jim on time. So that's what the numerator and denominator works out to, and I didn't round it to 3 decimal places because it terminated at 4, so that's 0.7695. So if there's anything here that you didn't understand, please make note of it and ask your teacher in class the next day. Thank you.